the idea of derivative is connected to the rate of change of a function. Here, we try to understand the idea of derivatives with the help of rate of change. We record the process of a free-falling body. The distance versus time graph of the body is shown here. The graph represents the function gt square divided by 2. Here g is a real number. The concept of the derivative comes when we wish to find the velocity at a particular instant. Suppose we wish to find the velocity of the body at a particular instant, say after a seconds. The position of the body at this instant is shown. The velocity of a body at any given time is given by the distance covered divided by time. The instant at a seconds is shown on the graph. Although based on previous experience, one could think of finding the value of the function against the y-axis against a. We wish to find the answer to a certain precision. This is where the idea of the derivative throws light. The velocity at a is given by this formula. If we move from the origin to an instant of time, say t1, we have the expression for velocity as shown. We continue this as shown. Now the velocity is as shown. Now, we come close to the instant of time, ta, at an instant, say tn. If we continue the process to an extent where we bring the interval very close, then we arrive at the derivative. In this fashion, the velocity of the body at the instant, a seconds, can be found accurately. In this module, you will learn about the concept of the limit of a function and the condition for a limit of a function to exist. Often, we encounter situations where we wish to find a point or situation where we are interested in a particular outcome. For example, let's consider the sequence shown. We want to find at what point in the sequence we get 1. If we observe carefully, to obtain 1, the sequence needs to be extended infinitely. Here is another classic example. We have an n-sided polygon inscribed in a circle. We have to find for what value of n will the area of the polygon become equal to the area of the circle. Let's start with the 3-sided polygon, the triangle. We can observe that the area of the triangle is not equal to the area of the circle. Next, we will increase the number of sides of the polygon. We increase the number of sides to 12. Still, we can see the distinction between the polygon and the circle. Now, we increase the number of sides of the polygon to 17. We can observe that the area of the polygon is almost equal to the circle, but not actually equal. As we keep on increasing the number of sides of the polygon, the area almost becomes equal to the area of the circle. This idea can be summarized. As n tends to infinity, the area of the polygon equals the area of the circle. This can be mathematically represented as shown. Or concisely as shown. Here, our target is to find when the area of the polygon will become equal to the area of the circle. This happens when the number of the sides of the polygon become infinity. We will extend this understanding of the concept of limit to functions. Suppose we have a function, x square, which is in fact a parabola. Let's observe the graph of this function. Here, our interest is to find at what point the value of the function reaches a certain value. Here in the graph, we wish to find the value of the function as x approaches any arbitrary point a. The mathematical representation of this idea is represented as shown. As the value of x approaches a, the value of the function approaches L. This is symbolically defined as shown. We read this as limit x tends to a, f of x is equal to L. Now, as an example, we wish to find what value of the function approaches as x approaches 2. We can observe that the value of the function approaches 4. Symbolically, we state this as shown. This means that as x approaches 2, the value of the function approaches 4. Once we have an understanding of the concept of the limit of a function, we can use the concept to analyze functions. To understand this, let's take the function that represents a parabola again. When we talk about x tends to a point A, we can approach A in two ways. We can approach A either from the right-hand side or from the left-hand side. When we find the limit from the left-hand side, we call the limit as the left-hand limit. Similar is the case with the right-hand limit. We represent the right-hand limit and the left-hand limit as shown. The superscripts on the top indicate whether we are finding the right-hand limit or the left-hand limit. For a limit of a function to exist, the left-hand limit should coincide with the right-hand limit. For the function x square, we will see what the left-hand limit and the right-hand limit are. The left-hand limit is as shown. On the left of the point 2, the value of the function is x square. The value of the left-hand limit is equal to 4. Similarly, when we find the right-hand limit, we follow the same procedure. On the right of the point 2, the function is x square. The value of the right-hand limit is 4. Thus, the left-hand limit is equal to the right-hand limit. Now we can say that the limit of the function exists and is equal to 4 at x is equal to 2. To understand this concept better, let's see this function. Let's see the graph of the function. Let's evaluate the limit of the function at x equal to 1. For the limit to exist, we have to verify whether the left-hand and the right-hand limits coincide with each other. First, we will calculate the left-hand limit. We took 4x plus 1. Since for x less than or equal to 1, the function is this. The limit of the function is 5. Next, we will find the right-hand limit of this function. If we observe to the right of the point 1, the function takes the form x plus 1. The limit is equal to 2. We can see that the left-hand and the right-hand limits do not coincide with each other. Therefore, the limit of the function does not exist at x is equal to 1. Let's see this graphically. At x equal to 1, the left-hand limit of this function is 5. The right-hand limit of the function is 2. We can see that ambiguity exists. Therefore, the limit of this function at x is equal to 1 does not exist. In this module, you will learn to evaluate limits at a given point. Here is the graph of a function. If we wish to find the limit of this function at an arbitrary point, all we have to check is whether the left-hand limit and the right-hand limit coincide with each other. Based upon this intuition, we will explore some functions. Let's find the limit of the function at 2. We obtain the values of the function very close to 2. The values are in the table here. In the table, the values close to 2 are 1.999 and 2.001. These are the points to the left and right respectively of the point 2. You can see that there is no significant change in the value of the left hand and the right hand limits. You can also observe that both the limits are approaching 5. This implies that the two limits coincide with each other and the limit of the function exists at 2. Therefore, we can assign the limit of the function at 2 as 5. This is evident from the graph. Next, we will move to a trigonometric function. The graph of the function is as shown. We will check whether the limit of the function exists at pi by 2 and determine the value of the limit. The table here shows the limit of the function close to the values of pi by 2. In the table, the values close to pi by 2 are taken with the difference of 0.01 to the left and to the right. We can observe that there is no significant change in the value of the left hand and the right hand limits. This implies that the two limits coincide with each other and the limit of the function exists at pi by 2. Let's take the value of the function intermediate to both the limits. Therefore, the limit of the function at pi by 2 is as shown. Now, we will see a two-piece function. The graph of the function is as shown. We obtain the value of the function very close to 2. The values close to 2 are 1.999 and 2.001. These are the points to the left and right respectively of the point 2. We can see that there is a significant shift in the value of the left hand and the right hand limits. This implies that the two limits do not coincide with each other and the limit of the function does not exist at x is equal to 2. This is evident from the graph. In this module, you will learn about the algebra of limits and calculate the limits of polynomial and rational functions. If the functions are well defined, then the limits of the sum, difference, product and quotient of functions can be found easily. Let's see how. Let f of x and g of x be two well-defined functions, and limit x tends to a, f of x and limit x tends to a, g of x exist. Then, the limit of the sum of the two functions is equal to the sum of the limits of the functions. We will verify this theorem. Let f of x be equal to x square and g of x be 3x square. Now, we verify according to the theorem for x tends to 1. First, we will find the limit on the left-hand side. Now, we verify the right-hand side. We can see that the left-hand side is equal to the right-hand side. The limit of the difference of two functions is equal to the difference of the limits of the functions. Let's verify this theorem with the functions shown with limit x tends to 1. The left-hand side is equal to -2. The right-hand side is also equal to -2. Hence, the theorem is verified. The next theorem states that the limit of the product of two functions is equal to the product of the limits of the functions. Let's verify the theorem with the functions while x tends to 1. First, we will find the limit on the left-hand side. Now the limit on the right-hand side is as shown. Since the left-hand side is equal to the right-hand side, the theorem is verified. If f of x is a constant, then we can write the relation as shown. The fourth theorem is that the limit of the quotient of two functions is equal to the quotient of the limits of the functions. Here, the denominator is not equal to 0. As in the previous theorems, these can be easily proved using the functions shown. We can see that the theorem is verified. Now, we will see the limits of polynomial functions. Based on the theorems that we have discussed, we will see how we can find the limits of the polynomial functions. A polynomial function is defined as shown. If f of x is a well-defined function, then limit x tends to a, f of x is equal to f of a. Let's substitute the polynomial in place of f of x. We can assume that each term in the polynomial is a function. Therefore, right-hand side can be written as shown. The first function is a constant. The second term also follows directly. The third term can be considered as shown. Similarly, the limit of the final term in the polynomial is as shown. This sum is equal to f of a. Now, we will see the limits of rational functions. A function f of x of the form g of x divided by h of x is called a rational function. Here, g of x and h of x are polynomial function. If we wish to find the limit of the function as x tends to a real number a, then we have these cases. A case where h of a is equal to 0 and g of a is not equal to 0. In this case, the limit does not exist. Another case is where both h of a and g of a are equal to 0. In this case, the limit takes the indeterminate form. In this case, we will remove the factors of x minus a from the numerator and the denominator. We can write the numerator and the denominator as shown. Here, two cases are possible. Either q is less than or equal to p, or q is greater than p. For case 1, the limit becomes 0. This is the determinate form. The limit does not exist for q greater than p. Let's try to understand the discussion by finding the limit of the function as shown. When we find the limit turns to be indeterminate. So, to avoid this, we write the numerator and the denominator in the factors of x minus 3. The limit is equal to 1 divided by 27. As a culmination, we will discuss a theorem on the limit of a function as shown. Here, n is a positive integer. We will prove the theorem. The numerator can be expressed as shown. Now, the limit can be expressed as shown. Now, the limit of this function can be found just like we find the limit of a polynomial function. This limit exists even if n is a rational number and a is positive. For example, look at the limit of this function. Evaluating the limits of trigonometric functions requires some techniques. The following theorems establish the ground for finding the limits of trigonometric functions. Let's take a look at these theorems. If g and h are real-valued functions with the same domain, and the value of g of x is less than or equal to h of x for all x in the domain, then for some a, the limit of g of x as x tends to a is less than or equal to the limit of h of x as x tends to a. This is obvious from the figure shown. Now, we use the result of this theorem for another theorem, called the sandwich theorem. The sandwich theorem is highly useful in finding the limits of trigonometric functions otherwise tedious to analyze. The theorem states that let f, g, and h be real functions, such that f of x is less than or equal to g of x is less than or equal to h of x for all x in the common domain of definition. For some real number a, if the limit of f of x as x tends to a is equal to L is equal to the limit of h of x as x tends to a, then the limit of g of x as x tends to a is also equal to L. In the figure, the curves in black represent the functions f of x and h of x. The red curve represents the function g of x. At point A, the limit of the functions f of x, g of x, and h of x is supposed to be L. Now, we will find an important geometrical proof that can be helpful in finding the limits of various trigonometric functions. In this geometric proof, the measure of x is in radians. We will take a unit circle. OQ is a line equal to the length of the radius. We draw another line, OS, making an angle x radians with line OQ. Here x should lie between 0 and pi divided by 2. We will draw the chord as shown. Now, we will draw a perpendicular from point S onto line OQ. The meeting point is P. Next, we draw a line from Q and perpendicular to line OQ. Extend line OS to meet this perpendicular line at R. We will get a relation from the figure, which is shown here. Here, all the quantities are real numbers. Therefore, the expression takes this form. In triangle OPS, we have sin x is equal to SP divided by OS. Since the length of lines OQ and OS are equal to the length of the radius, we can replace OS with OQ in the denominator. Also from triangle OQR, we have tan x is equal to QR divided by OQ. Hence, QR is equal to tan x multiplied by OQ. We will substitute these two inputs in the relation. Since OQ is positive, the relation can be represented as shown. Since x lies between 0 and pi divided by 2, sin x is positive. Dividing throughout by sin x, we get the expression as shown. Taking reciprocals, we arrive at the expression shown. Here, we can see that the function sin x divided by x is sandwiched between cos x and 1. Here, we will see two important propositions that can be used in finding the limits of trigonometric functions. For the function sin x divided by x, we can use the sandwich theorem. We will use the relation shown. We will find the limit of each function in this relation. At 0, the limit of the function cos x is 1. The limit of the constant 1 is 1. Therefore, the expression takes this form. Therefore, according to the sandwich theorem, the limit of the function sin x divided by x is sandwiched between 1 and 1. Let's look at the second proposition. We will use some relations from trigonometry. We will rearrange the expression of the function as shown. As x tends to 0, x divided by 2 also tends to 0. Therefore, we can write the limit in the first expression as x divided by 2 tends to 0. By the sandwich theorem, the limit in the first function is equal to 1. The limit of the second function is obviously 0. Therefore, the second proposition is proved. The concept of derivative is used extensively in science and engineering. We will explore the concept first by looking at the definition of a derivative. Suppose f is a real valued function and a is a point in its domain of definition. The derivative of f at a is defined as shown. The derivative is defined provided the limit exists. Derivative of f of x at x equals a is denoted by f dash a. To understand the definition better, we will see an example. Find the derivative of the function given at x is equal to 2. The derivative is found as shown. Now, we will simplify the numerator. Therefore, the derivative of the function 2x plus 3 at x is equal to 2 is equal to 2. Now, we will look at the geometrical interpretation of a derivative. Consider a function f of x. The curve here represents the function. Let's consider a point P on the curve. The coordinates of the point are a and f of a. Let Q be another point near P on the same curve as shown. The coordinates of point Q are a plus h and f of a plus h. Now, draw perpendiculars from points P and Q on the x and y axes. If we consider points P and Q, the increment along the y-axis is f of a plus h minus f of a. The increment along the x-axis is a plus h minus a. Now, according to the definition of the derivative at a point, we have the expression as shown. In the figure, this is equivalent to QR divided by RP, where point Q tends to P. The ratio in the limit is equivalent to tan QPR. This means that chord PQ tends to become a tangent at point P. Now, the limit is equal to the slope of this tangent. Therefore, the derivative of the function at point P is equivalent to the tangent of the angle made by the tangent of the curve with the x-axis. From this, we will state another definition of the derivative of a function. Suppose f is a real-valued function. The function defined by f-x, wherever the limit exists, is defined to be the derivative of f at x. This definition of a derivative is also called the first principle of derivative. Let's see an example here. Find the derivative of the function given. The derivative is found as shown. Now, we will simplify the numerator. Therefore, the derivative of the function x squared is 2x. Often, a function can be expressed as the sum, difference, product, or quotient of two or more functions. We will see how the derivatives of these functions are found. Let f of x and g of x be two well-defined functions. The derivative of the sum of two functions is equal to the sum of the derivatives of the functions. Let's verify this theorem with the help of an example. Let f of x and g of x be as shown. We will first evaluate the left-hand side of the theorem. Note that the derivative of a constant multiplied by a function is equal to constant times derivative of the function. Now, we will evaluate the right-hand side. Hence, the theorem is verified. The derivative of the difference of two functions is equal to the difference of the derivatives of the functions. Now, we will use the same functions that we used earlier. We will first evaluate the left-hand side. Now, we will evaluate the right-hand side. We can see that both the sides are equal to each other. The theorem is verified. The derivative of the product of two functions is as shown. In this case, rather than verifying the theorem, we will see how the theorem can be used effectively to evaluate the product of two functions. We will find the derivative of the function x into x plus 1. This function can be expressed as shown. Now, the derivative of the function is as shown. The derivative of the quotient of two functions is as shown here. This theorem will be useful when evaluating functions of the kind shown here. Let's find the derivative of this function. This function can be represented as a quotient of two functions as shown. Now we find the derivative. Often, we are required to find the derivatives of polynomial functions. A polynomial of degree n is as shown. We can observe that the polynomial consists of the variable x raised to various powers of n. We will see a theorem about the derivative of x power n. We will find the derivative of this function using the first principle. From the binomial theorem, x plus h whole raised to the power of n can be represented as shown. Therefore, the numerator can be represented as shown. Now, we use this in the derivative formula for f of x. Eliminating the common terms, the derivative can be represented as shown. As h tends to 0, all the terms containing h on the right-hand side vanish. Therefore, the derivative of x power n is equal to nx to the power of n minus 1. The same result can be achieved by using the product rule. X power n can be represented as shown. Now, we will find the derivative of x power n. Using the product rule, this can be represented as shown. If we observe the second term, we can see that it contains the derivative in the form of x power n. Using equation 1, we can write the derivative of x power n minus 1 as shown. In a similar fashion, we can write the derivative of x power n minus 2 as shown. In the same manner, differentiating successively up to n times, we get the form as shown. Therefore, the derivative of the function x power n is equal to n multiplied by x to the power of n minus 1. This is applicable even when n is real. As an example, let's find the derivative of the function f of x as shown here. Now, we will see a theorem on the derivatives of polynomial functions. A polynomial function of degree n is defined as shown. Here all the coefficients are real numbers. The derivative of this polynomial is as shown. The proof of this theorem is based on the theorem we just saw. First, we express the derivative as shown. This is because of the theorem on derivatives. Now, we will evaluate the derivative of each term. As an example, let's find the derivative of the function g of x as shown. Here, since the function is a polynomial function, we can directly apply the theorem. Hence, the derivative of the polynomial function is as shown. The derivatives of trigonometric functions are unlike the derivatives of algebraic functions. Let's find the derivatives of some trigonometric functions using the first principle method. First, we will find the derivative of the function sin x. Let's apply the first principles method. The numerator takes the form as shown. As h tends to 0, h divided by 2 also tends to 0. Now, we can rearrange the function as shown. The first term in the product becomes cos x. The second term becomes 1. Therefore, the derivative of sin x is cos x. Now, we will find the derivative of the trigonometric function cos x. The numerator takes the form as shown. As h tends to 0, h divided by 2 also tends to 0. Therefore, the derivative of cos x is minus sin x. Now, we will find the derivative of the trigonometric function tan x. As we have done before, we will use the first principle method as shown. The function can be written in the form of sin x and cos x. The numerator can be simplified using the formula. This can be arranged as shown.